Hello everyone. Welcome to our webinar, Get Deep Learning Framework Performance on Intel Architecture. Our presenter today is Nathan Grenelch. Nathan is a data scientist and machine learning engineer at Intel. During his presentation, we will have another content expert answering questions in real time, and Nathan will answer some questions at the end of the presentation during our Q&A session. A PDF of the presentation is available on the resource list at the bottom of your screen now. And with that, we will turn our time over to Nathan.
Thanks for the introduction. The title of today's talk will be Get Deep Learning Framework Performance on Intel Architecture. And I hope to sort of get our strategy across to you, what Intel's trying to do, and also how you can get these accelerations and get your code up and running quickly and easily. So the talk's on deep learning. Deep learning is an aspect of the field of AI, or artificial intelligence. Most of you should be familiar with this, or you likely would not be at the talk today. But Intel, just like everybody else right now, understands that this is probably going to transform almost every piece of the economy, right? So this is consumer, health, finance, all these different sectors will be affected. And the way the part of AI that this talk is going to cover, is deep learning, machine learning, those kind of things. And the goal of all these efforts is to gain worthwhile insights from the data, maybe predict some outcomes, maybe direct change inside an org. If you can model something to say we can do things better this way or that way, and hopefully get action and response, and that's where the transformation will come. So at the same time as artificial intelligence is growing and widening, the amount of data that we're collecting and storing is exploding, right? So one of the questions is how do we process all of this data? The type of solutions to get this job done are in the memory space, connection speed, and as we will discuss in this talk, fit time. So if you're trying to model something based on all this data, the faster you can fit to it, the better. So if we look at Intel's AI strategy, it's probably best encompassed in this quote: artificial intelligence everywhere. So we want to work both in the software and the hardware space, and all different types of hardware and different types of software libraries to get our solutions to the public. We have announced work on discrete hardware, and we're working diligently towards this. So this is things like GPUs, FPGA, and VPUs. So these type of processing units are maybe not what Intel's known for, but this is the direction we're pushing. But at the same time, we are not getting away from our roots, right? So we have our CPUs, we have our Xeon line, and we are adding things to target directly at AI, directly on the hardware, I should say. We have a launch in a couple weeks for our codename Cascade Lake, and it has a piece to it called DL Boost. It's a bundle of accelerations for AI, and we'll add things to the DL Boost as the processor matures even further. But us designing DL Boost and putting it out sort of shoots home the point that we really are building AI into our hardware. But we're not just doing the hardware side, we're working on the software side as well. So if we look at the software strategy, which is hopefully one of the most important parts of this talk and why you're here today, we are accelerating popular frameworks. So Intel has a couple in-house inference or training libraries called BigDL and OpenVINO, but we're also working on hiding our math underneath popular frameworks like TensorFlow, PyTorch, and MXNet. So we know that a lot of the customers and users want to work in Python. They want to work with their most comfortable framework, put it that way. And so instead of trying to pull that behavior away and come up with yet another framework, we are jumping on board and, like I said, hiding our math underneath. So we have these libraries, MKL and MKL-DNN. MKL stands for Math Kernel Library. It's fairly popular in the field of HPC and many science and engineering fields as well. It's just fast math primitives. And MKL-DNN is an offshoot of that. It's actually gone its own way in the last year and a half, and it's just focusing on fast primitives, get the math done quickly. So that's underneath the framework. So there's internal teams writing MKL-DNN, of course, right? That's an Intel piece of software, but there's also internal teams that are only focused on integrating MKL-DNN into PyTorch or into MXNet or into TensorFlow, and then working with the main repos to upstream them. So this talk, when we talk about frameworks in the rest of the talk, this is what we're talking about. This optimized TensorFlow, optimized MXNet, optimized PyTorch with Intel optimizations. If we zoom in on the frameworks, there's not much to say here, I guess, but I just want to show that we have an ai.intel.com and a website that's for just framework optimizations, right? So you can go to this website and pick your favorite framework, and it will give you links to installation, getting started, those kind of materials. So you can really come and hopefully get pointed in the right direction early. And it's ai.intel.com/framework optimizations. The topics I'll cover today are on the screen, and I'll start by defining the problem. Then I'll get into some hardware solutions. The title of the talk is Deep Learning Frameworks, so I'll spend more time on the next topic, which is the software solutions. And then I will discuss at the end how to get the frameworks and the resources available. I put the how to get at the end on purpose, and I want to stress that that's a very short section. And if it was any different, then we wouldn't be doing our job right, because we want to make it easy for you to get these and get up and running. So how to get the frameworks will be very quick and clear and hopefully not confusing. So we'll start with defining the problem. This is how Intel sees artificial intelligence and machine learning. So deep learning is a piece of machine learning, which is a piece of artificial intelligence. This is where sort of deep learning fits in Intel's mindset, and this is sort of what we work towards in the deep learning teams. This is how we orient ourselves in space. More specifically, if you look at the types of machine learning that's out there, there's training and inference in both cases, right? You want to train a model, then you need to deploy it and actually use it to get something done. But there's a whole branch of machine learning that's now called, I think, classical with a lot of people in the field. These are things like classification, regression, and these sort of techniques that have really blossomed recently as well, just like deep learning. But they're their own separate, field, its own separate genre of analysis. And Intel has a library focused on those. It's called DAL. It's Data Analytics Acceleration Library. So if you're interested in that kind of analytics, please check out our DAL library. But that's not what this talk's about. This talk is focused on deep learning. So if we zoom in on the deep learning part of the table, this is what we're talking about, right? So this deep learning is, let's say, chaining together multiple layers in a topology-like form and connecting many pieces of the layers together in some sort of interesting combination that you think will help solve your problem statement, right? So you could see that the number of layers can get out of hand, right? The number of connections get out of hand, and it becomes a optimization problem very quickly, not just in the prediction accuracy side of things, but also in the performance and the fit time. So most of the accelerations Intel's working on is in the fit time side, because if you can't fit it, then you can't use it, right? So if we get to look at sort of why deep learning is doing what it's doing right now, why it's having such a moment, I think these plots can help with that, right? So if we look at the popular use cases like image recognition or speech recognition, the deep learning strategy for solving problems has gone from not reliable to reliable in the last couple decades. The human beings can look at a certain number of images and get some sort of prediction accuracy, right? And deep learning networks used to be lagging fairly significantly behind human recognition. But over the time, in the last 20 years or so, that's really fallen precipitously, and the prediction error for deep learning is easily surpassing human recognition at this point. And then if you can add to the fact that you can process 10,000 images, where a human can maybe look at 100 of them in an hour, that's a significant increase in quality. So why is the error dropping? The networks are better designed, right? So like I said, there's, a deep learning network is some layers chained together with some smart connections between them. So we're getting better at designing the types of layers and how to connect them. And in return, we are getting better prediction accuracy. And also more data can be processed, right? So the more information you can put in it, a neural network's just a mapping function like any other classical machine learning function. So you're trying to map an input to an output. If you have a good mapping function, it does a good job of taking information and turning it around to mean something useful at the end. The more information you can put into that useful mapping function, the more good information you get out the other side, right? So the fact that we can process more data, maybe fit quicker, as I'm talking about in this talk, also contributes to the lower classification error. If we want to track the depth of layers, and this will, push more towards why we need to fit faster, why we need to infer faster, all pieces of the pipeline. So if we look at the ImageNet classification contest with the top 5 error rates are the bars on the plot. You see from 2010 to 2015, the number of layers that's going right to left has risen. So it's up at 150 layers. So you can go back to that plot I had or that image I had of a network and imagine it being 152 layers deep. But the classification error has dropped, like I said, precipitously with this added depth. The added depth brings on many more layers, of course, but it brings on many more connections. So if you are training or inferencing, you have to have many more pieces of math, primitives of math that have to run and execute in order to get the job done in a timely manner. So it's natural to see the depth rising and think, maybe I need to accelerate my code or accelerate my execution, right? So a thought has jumped into the minds of many people working in the field that you have to have a GPU to do this. And it's Intel's opinion that this is mostly myth. And we come to this from talking to customers and enterprise users. And they tell us that most of them, they use CPU for AI and deep learning. The people in the field who are making decisions based on resources and efficiency usually have some sort of inflection point that they've defined, that after they reach that inflection point, then it's time to try to bring in an accelerator, right? And that makes sense. So part of Intel's strategy in addressing this and trying to make this myth go away is to take that inflection point and move it up. So if you imagine the perf requirements is the y-axis on this plot, if you can move that up higher and higher and higher, the inflection point is met less. So accelerators are not jumped at by people in the field. And we want to do everything on Xeon, of course, right? So if we can go higher and higher, maybe we can get the inflection points to disappear, right? That's the strategy. So we have, like I said, we have a Cascade Lake launch very soon. So I'm going to stay away from a lot of performance numbers in this talk. I think you see a lot of performance numbers in Intel talks, but there's a very good reason it's not happening this time, because there's some stuff we can't give out yet to the public, and this will become stale right away. And the performance numbers are honestly not as important to the message. I want to get across that we're doing framework accelerations and that we care about targeting the hardware at these AI workloads, and that can be done without showing performance numbers. That being said, the performance number I will show is this trend, right? So this shows what we did on Skylake, which is the bottom left of this plot, and where we're going in the Cascade Lake side, which is the top right. So if we look at Skylake, we started with FP32, inference and training. We had some sort of speed, some sort of performance number, right? And then we worked on software optimizations, like I'm going to talk about in the rest of the talk, with new library and framework optimizations to get up to 2.8x better, right? And then we enabled int8 support with new instruction code, and we wrote the frameworks towards those instructions. And then we got the speed up even higher. So this strategy of not only software but also hardware changes is how Intel is addressing this problem. And when we go to the Skylake portion of this plot at the top right, I want to show that we're going in the same direction, right? We're going to do the same thing. So hardware and software occurring when Cascade Lake is launched. So the next topic covered is the hardware solutions, or the way we're addressing this with hardware. The software side should be a little longer because, like I said, the title of the talk is Get Deep Learning Frameworks, but I want to get the message out that we are also building hardware directly at these problems. This is a common message if you've been to other webinars from Intel or if you read press releases, right? We have a Xeon scalable processor that we're very proud of. It's targeted at data centers and just running HPC workloads very quickly. We want to plow through numbers as fast as we can. Plow through analysis numbers, I should say. So we work on performance improvements all the time. We write software towards the hardware, to our own hardware. So if you buy our hardware, you can expect to get software that runs fast on it. We add lower precision integer ops and scaling efficiency. If you buy a Xeon scalable processor, you will get software written for you to run fast on your hardware and exploit it to its fullest extent. That's the main take home. So one of the examples is, I know these are instructions, so it can be argued whether this is hardware, software realm, but it's close enough to the metal that I consider this hardware, at least for the purpose of this talk. So the instruction set 512 is instructions we have to run on our wider 512 register. So we have vector register it's bigger, and we're more proud of it. We're proud of it more than we've been in the past, right? And we have instructions built directly for this, of course. These numbers are all Skylake, so they're not so relevant moving forward. But I just want to show that this is targeted directly at AI type workloads, and it helps run faster. We added int8 support. So these are instructions to run inference or inference type math with int8 support. And what int8 does is, of course, allows you to get more operations per cycle, which means you get more math done in a given time, of course, right? So this has also been brought in during the Skylake generation and will continue on into Cascade Lake. I'll go back to this plot because I just mentioned AVX 512 and int8 support. I want to highlight now this deep learning boost that I mentioned earlier. So deep learning boost is a sort of bundle of stuff to make AI run faster on your machine, right? And one of the things inside at launch inside this bundle is VNNI. So these are vector neural network instructions, or VNNI, and they are another set of instructions, like the name says, targeted directly at neural networks. So this talk in the future, we'll be able to discuss more specifics about VNNI after the launch happens. Now let's go back to our neural network side of things. So if we look at this network with multiple layers and multiple connections, we can see that it gets ugly quick, right? So you have to go forward through the forward pass, and that's inference. And you have a loss function at the end of it. You find the derivative of it. You run back through with backward propagation. And that's one full step of the training process. But then you iterate and do it over and over and over again. And since these networks can have billions of parameters, this like I said, gets ugly fast. It blows up. So what we need to do is try to reduce the time to train, reduce the time to infer, all these types of things are essential to getting this technology to deploy at its fullest. So one way to process more data is to, of course, just optimize raw performance. So this is floating points operations per second. And this is where a lot of people see Intel, right? So when you think about Intel, there's a large part of the population that still just looks at us as, pounding performance and working on optimizing that. And I want to make sure that it's understood that we are still doing that. That's a piece of Intel. That's still a huge piece of Intel. But it's not our only domain anymore. Another way to process all the layers faster is to, of course, scale out. The idea here is use distributed learning to tie together multiple nodes and have all of them plow through their own portion of the data or their own portion of the training simultaneously, and of course you can get more done. If you use a scalable topology with a scalable library, and you have a nice scaling efficiency, it's almost one-to-one, right? So you have to design things properly, of course. But if you do it correctly, you can really get a nice impact on your train time and your inference time. So Intel's currently, I listed maybe 6 or 7 frameworks at the beginning of this talk, and Intel's investigating what we want to recommend as the scaling library for a given framework or scaling strategy. But there's a couple that we've already decided on. So on the Caffe side and the TensorFlow side, we've taken a decision and we are providing materials to help people get off the ground with these scaling libraries. Both of them are based on MPI. The first one for Caffe is an Intel internal library called MLSL, and for TensorFlow, we use an external Hoverod library from Uber. But as time goes by, we have a nice initiative inside the company to decide on what we want to recommend to customers for each one of the frameworks to get it to distribute running fast on CPUs, and we'll roll that out as we solidify the plans. So now I'm going to talk about the software side, and this is where the frameworks come in. People used to ask, what's under the hood for running your HPC code? And I think a lot of times under the hood would mean hardware, right? But if you're in the machine learning space, the AI space, you are typically working in a higher level of abstraction, right? So a data scientist or a machine learning engineer is trying to solve some sort of prediction problem or look for some insight, and they have to be in that prediction space in order to get the job done properly, right? That's the abstraction space they need to be in, which is much higher than let's say, the hardware underneath. So because it's a higher level of abstraction, there are libraries underneath those level of abstractions in between the API library and the hardware now, right? So under the hood actually means other pieces of software, right, if you're in the machine learning space. So when I say what's under the hood for these frameworks, the answer is a primitives library called MKL-DNN that I mentioned earlier. And this library is targeted at deep neural networks. It's in the name, and it's just a primitives library. So like I said, it makes small little pieces of math primitives. So if you think of a topology chaining together little segments of math sequentially to solve a problem, this library has each one of those segments. So it has something like a convolution, a ReLU, a pooling layer, right? And it's optimized directly for the CPU. So that's what this library is. It has int8 support. It has full FP32 support, of course. It has 2 threading types, OpenMP and TBB. So TBB is Intel's internal threading, and that will take care of a lot of oversubscription or thread fighting issues when you're running your execution. OpenMP is a little more widely used, of course, and so we have full functionality in MKL-DNN for OpenMP. And most of the frameworks write their code with OpenMP version of MKL-DNN. So that's what you'll get if you, let's say, download TensorFlow or MXNet from us. So you transition into the frameworks. I want to be clear that a lot of these primitives are built with old-fashioned vectorization. So you can, if you went to programming school, you learned what vectorization does for plowing through math quicker. But we also are targeting our new vector registers, right? Our wider vector registers. We are doing things like reusing data when needed or when possible, and we're parallelizing pieces of those math. So we turn a primitive into a routine almost, and then we run through it quickly. So all these, if they're underneath your framework, you're getting this for free. Even the integrators that work on the frameworks are getting this for free because it's inside MKL-DNN. So the frameworks themselves, I'm going to give a few examples of what our framework teams do. So I said we have Intel optimized TensorFlow, Intel optimized MXNet, and we have this primitives library, MKL-DNN, that runs through neural network math fast. So now I'm going to discuss what the framework teams do. So that means if you work in the Intel TensorFlow team internally, uptaking MKL-DNN code into TensorFlow, this is what you do, right? So that's what I'm trying to cover. So the first one, a good example of what they do is fuse layers. So MKL-DNN knows that there's common chaining it together of layers that happen in many topologies. So MKL-DNN provides fused versions of layers. So in this example, we have a fused version of convolution 2D with bias. So the framework team will write code that identifies the best places to fuse, and then it will do that for you under the hood and call the fused version of the MKL-DNN primitive. So this is a good example of graph optimization, right? So our framework teams are letting you define an execution graph or an execution step and chaining together steps. And then when the execution graph is built, our framework team sort of interjects, jumps in there, and optimizes the graph for you. Another thing we'll do is layout conversion. CPUs we have found is a better way to say this. We have found there's a nice data layout that CPUs like to use for their math calculations. That's the best way I can say it. So we have a layout that is optimized for CPUs. And MKL-DNN, of course, has written their primitives to run faster on those optimized layouts. But as a user using TensorFlow or MXNet, Caffe or PyTorch, this doesn't concern you, right? You have your own input data, your own sort of data layout, and you're coming in to the framework. So what our framework teams do is take that input, maybe in CHW, those kind of things, in HWC, whatever it is that you want to come in with, and we'll convert it for you. So when we build the graph, we'll add conversions in there to convert it to CPU-friendly format and then act like everything else, run quicker. Another important step is that we don't only just convert. I want to make it clear that we do our best to convert at the beginning and then convert at the end. So we want to convert to a CPU-friendly format, and then we want to sequentially plow through as many layers as possible in that format and then convert back at the end. Again, the user doesn't see this. So if you're using our TensorFlow, you don't know that we're doing this under the hood, but we are. So we'll chain together multiple primitives with the CPU format. You'll never know it's happening, but we're making the code run faster and faster. We've also done work with load balancing. So if you've used TensorFlow, you have undoubtedly, if you were monitoring performance at all, you've undoubtedly seen that there are subscription issues, there's thread issues that come up when you run large sessions with TensorFlow. So our framework team actually works in the TensorFlow layer to remove some of those, even before it gets to MKL-DNN. We read the normal TensorFlow arguments, so interop parallelism, these are TensorFlow flags that you can pass. But also, for the MKL-DNN side, it's very important to set the open and P number of threads. So this tells MKL-DNN sort of how many threads it has at its disposal, and then the framework team's orchestration code written around that will work on load balancing for you. You won't have to think about it. Again, if you tried to measure performance on TensorFlow, you've run into these problems. If not, just know that we are fixing them under the hood for you. So as I mentioned earlier, I'm going to end the technical portion of the talk talking about how to get the frameworks. There's not going to be much to this because we want to make it easy for you. And I hope it comes across that way. So first, I mentioned earlier, we have this intel.ai/framework optimization site. So if you want to learn how to install, let's say, Intel's version of Caffe, it's listed on this site, but also PyTorch and TensorFlow and MXNet. So if you go to this site, you can get the install instructions for any of these frameworks. Again, hopefully making it easy for you. So I've shown an example here of how to get TensorFlow. So we have multiple distribution packages with hopefully the idea of going to the user, right? Where do you want to be? Where do you want to get your packages? This is where we're going to go. So in Conda, we are in the main Conda channel. We worked very hard to get there, but now we're in. So if you go to the main Conda channel without specifying anything else, you can get our version of TensorFlow. Also, if you go to the Intel channel, of course, since we control what's on the Intel cloud, we have a version of TensorFlow. I should say that the main channel for Conda has a slower cadence of uploads, right? So they have some sort of schedule that you need to follow and checks and balances on what goes into the main channel. Whereas the Intel channel, we put in whatever we want, whenever we want. So we have our own internal checks, but the Intel channel, we can put our most recent version of in right away whenever we want. So if you go to the Intel channel, you get the most up-to-date version of Intel's TensorFlow. So I would recommend going to the Intel channel, but we're also in the main channel. We have a pip version. We have Docker containers. And of course, you can always build from source. So if you go to the TensorFlow build from source instructions, there's a section on CPU. And I don't remember if it calls out MKL or not, but the CPU instructions are just how to build the MKL-DNN version, even if it doesn't say those words. Another one I'll show is MXNet. So MXNet, we don't have as many distribution channels, but we do have a pip install for easy package management. And users of Conda should know that they could do a pip install inside a Conda environment. We also have instructions on how to build from source. So if you want to go that route, you can do the same. I'm not going to cover each one, but like I said, we have intel.ai/framework optimizations that covers each one of the frameworks. But they're all this sort of thing. You either build from source or you get it from an easy binary package manager. Now I'm going to cover resources available. So this is probably the most important part of the talk, honestly. Deep learning is a tough field. Machine learning in general is not, the easiest. Maybe the basics are easy, but solving problems with it's hard. And when you get to solutions that require a bunch of computations and you need to run fast, it gets even harder. It's sort of an overlap between the machine learning high-level abstraction space of solving a prediction problem with HPC level code acceleration problem, right? And that is requires a very specific set of skills that we know not everybody has coming into this. So we provide lots of resources for you, and hopefully you find them helpful. The first resource I want to cover is a plug. This is a shameless plug of an article that I'm the author of. So this is called Maximize TensorFlow Performance on CPU. Basically, I go into all the flags you might want to set or settings you might want to tune to run fast on a CPU inside Intel optimized TensorFlow. I don't just give the flags or the recommended settings, but I also explain each one. So you can use this to get up to speed on what the flags are and what they mean and why they're important to tune. And it's called TensorFlow in the title, but 80% of it is MKL-DNN specific stuff and CPU specific stuff. So this information scales to the other libraries. So if you are working with Intel MXNet, 80% of this article will help you optimize your code. So please feel free to try to digest everything. I'm available. I'll talk about a forum in a minute. I answer questions on our forum. So if there's questions about this article, it's my baby, and I'll answer directly on the forum for you if something's not clear. Just let me know. We also have a rebranded version of our AI Academy called AI Developer Program. So it's spread out to cover builders and developers programs that we've put together along with the AI Academy. The website is software.intel.com/AI. And all the AI Academy stuff is still up there. So if you want presentations or getting started type beginner material, it's there. If you need more, let's say, higher level stuff for builders or enterprise developers, you should also be able to find it at this site. As I mentioned earlier, we have a new AI frameworks forum. We're trying to get it off the ground and get some traffic on it. So I have the first post here. I screenshotted it to show you how recent this is, February 6th. And as I said, I'll answer questions directly on this forum. So if there's any questions about the frameworks or any of the other pieces of resources that I'm trying to give to you now, feel free to come there and ask, and I will answer. You can get to this forum by going to forums.intel.com and hunting around the title list to look for our forum, which is called Intel Optimized AI Frameworks. Unfortunately, the link is very long, so I can't put the full link up here. But if you go to forums.intel.com, you should be able to find Intel Optimized Frameworks fairly easily. We have a program called Intel AI Builders. It is for enterprise customers that want to work with us to optimize their hardware, right? So it's strategic in nature. You have to be accepted into it. But if you're in, we work very hard on whatever your problem statement is to push accelerations for you, try to help you solve your problems. We work in the solution space and in the performance optimization space. The list of companies is on the slide. It's very long. You likely know about this already if you're a candidate, but if not, and you think you may be a candidate, it's builders.intel.com AI, and there's some good materials there for you. Also available on that builders.intel.com website is our solutions library. So we've had companies that we've worked with agree to help us write white papers about their use case and how the solution worked for them. So these white papers will cover very detailed solutions and how they were thought through and how they were put together and how they helped the company solve the problem. These are available on the builders.intel.com website. So the next steps is go to intel.ai.com/framework optimizations. I've said that site probably maybe 8 or 9 times already. And that's where you can start. And like I said, there's a section for each framework. So if you come in and you only care about MXNet, and then click on the MXNet link. Then get going with our libraries, right? So get them downloaded, run them on your code. You shouldn't have to change your code to get them to run. You can look at my performance doc, the one that I plugged to maybe optimize that code, but you shouldn't have to change your code to run. We're working very hard to optimize other people's frameworks, right? We're optimizing TensorFlow. We're not optimizing Intel's alternative to TensorFlow. So you should be able to use your TensorFlow code to run and hopefully not have a bunch of problems. If so, we've done our job wrong, and you go to our forum and bang on us and have us get it fixed, right? And I keep talking about forum because I want to tell you guys that we're going to be very responsive to this. So this deep learning framework optimizations and AI as a strategy at Intel is a very big priority. And we have a team whose job it is to not only evangelize for this, but help people get off the ground, solve low-level, high-level problems for them, and help them get their code running faster. So we're paid to be responsive to this kind of stuff. And it's not just tech support, it's high-level support to answer any type of problems that you're having. So go to forums.intel.com, and we can get engineers and dev engineers to give you that level of answers if that's required. And, if something is not working for you, bang on us. We will be responsive. We will get it fixed. And if we do this for a little while, we will have products that fit you, right? That you want. So please use these forums and help us make this better. And that's the end of the talk. I'll leave the call to action slide up instead of going here if you guys want to jog down the sites. Thank you.
Great. Thanks, Nathan. That's the end of the presentation portion of the webinar. Before we start the Q&A portion, I wanted to let everyone know that there is a survey at the end of the webinar. We would appreciate it if you would fill it out to help us improve our webinars and provide the right content to you. This presentation is being recorded and will be emailed to you later this week. The recording will also be available on Tech Decoded by the end of the week. And now we will start the Q&A session. There's lots of good questions that have already come in, but feel free to use your chat box on the bottom of your screen to ask any additional questions now. We should have a good amount of time. So I'll just start at the top of the list. Can we use Intel optimized TensorFlow with other tools for optimization like Horovod?
Yes, I tried to call out Horovod specifically earlier in the talk. And like I said, we are deciding on what we want for distribution, what we want to recommend. But for TensorFlow, we've already made the decision, and Horovod is our choice. So, not only specifically for Horovod, but we are not breaking integration for other tools. If it breaks at the CPU level, that's a different story. But we're not breaking integration. We're writing for TensorFlow. So if you're integrating TensorFlow into other code for whatever decision or whatever reasoning you have, we're not going to break that. Right. Before we jump down into our graph optimizations, the TensorFlow graph is still built. So if you have some sort of code that maybe is going underneath the API level, a layer of TensorFlow, and checking out the graph that was put together, that graph is still built by TensorFlow to start with. So those sort of our integrations are not breaking those kind of things, is what I'm trying to say.
Thank you. How is the accuracy handled at the Int8 precision level?
That's a tough question to answer. So we have, so MKL-DNN is a primitives library, right? It is, from their point of view, it's up to the user to deal with any sort of orchestration or any sort of prediction issues, right? So that's the MKL-DNN side. The TensorFlow integration team is a different story. For MKL-DNN, we provide Int8 for you, and it's sort of the developer's decision whether the accuracy is good enough, right? Because you're going to lose accuracy. You can't get around that. You lose precision. You lose certain numbers in your range that you can predict towards. So you're going to lose accuracy. The TensorFlow team they're closer to the user space, to the solution space. So they have to, they can't just get away with saying that, right? So users care about accuracy. So does our TensorFlow team. So from the framework optimizations point of view, we are taking the strategy of going through popular topologies, for instance, let's say ResNet 50, and deciding whether our Int8 support that we can add is sufficient. So you can think of us as turning on Int8 from MKL-DNN, measuring the accuracy drop, and comparing it to our best prediction accuracy, or maybe the best published classification accuracy for these models. And if it falls below a threshold that we've defined, then the TensorFlow integration team will work in the TensorFlow layer or the non-MKL-DNN layer to see if they can up that a little bit. And then the decision's made to sort of promote us having an Entei version of that topology, if that makes sense. So we're aware of it. We can't make the decision for you on whether the drop in accuracy, or the drop in precision, I should say, is a better way to term it, matters. But it is on our radar, and we're not just blindly throwing low precision inference on problem statements that they may not, be appropriate for.
Thanks. This one says about Caffe. Is there a version optimized from Intel like TensorFlow?
Yeah, Caffe is the one that I think we even call that one Intel Caffe because we have the most extensive, actually, framework optimizations for Caffe. And a lot of the developer and engineers internally will talk about Caffe when they go external, and they'll focus on it because that's the best performance we have to tout. So if you're a Caffe user, I would say that you are in good shape with Intel's version of Caffe. Go to the same site, the intel.ai/framework optimizations, but trust me that if you run Caffe, you'll get the fastest we have to offer. We're pretty proud of it.
Great. Does Xeon Skylake have instruction set that supports int8 inferencing? Is it the same as VNNI for CLX?
So the first question, does Skylake have int8 support? Yes, it does. So Skylake's a generation, and there's multiple processors in the generation. And more and more support was added as the generation matured. All that support will be translated directly to Cascade Lake. So Cascade Lake will have the full int8 support out of the gate, or at least what we're calling full right now. We can always add to it. The VNNI is separate from that. So VNNI is a set of instructions that are targeted directly at AI, right? Yeah, that's probably about all I want to say on that. But they're not the same thing. int8 was added before VNNI was even finalized, right? And that's why I put the int8 stuff in the Skylake side of the talk, or the Skylake side of the plot. And I hope I didn't confuse listeners.
Okay. Is Intel optimized TensorFlow supported by OpenVINO to obtain the IR model?
Is Intel optimized TensorFlow supported by OpenVINO? So I believe our interchange format we bought into is Onyx, and since TensorFlow is compatible with Onyx, since OpenVINO can take Onyx in, I think the answer is yes. I don't know. I maybe would want to talk to the questioner and maybe get specifics of what they mean by the question. But if you're comfortable using Onyx as an interchange format, then they're definitely compatible.
Cool. Is the TensorFlow version Nathan is talking about on GitHub?
TensorFlow version. So we upstream our changes. This is a complicated question, so I guess it's good to ask. We upstream our changes to the main TensorFlow repo. So we're a contributor. We have a user ID, TensorFlow-MKL. You can submit questions directly to that if you'd like. But we submit PRs directly to the main Google repo. So all of our accelerations are directly in that repo. That doesn't mean when you build TensorFlow, you get all of them, because there's build flags to build certain types of binaries, right? Just like any other piece of software. So even though our accelerations are all in the main repo, that doesn't mean that's how you get them. We have distribution channels, Conda, pip, and we will take the entirety of the TensorFlow code and we will build with the proper flags to bring all of our CPU accelerations to the forefront. So if you get it from Conda or pip, you will get those binaries pre-built for you to do that. If you build from source, you'll start with the main Google repo because we have our accelerations there. But while you're building, you'll have to take care to do it properly to get the CPU accelerations actually active in your executable program. And of course, we know that this is sometimes tedious, the building from source side. So if you've decided to build from source, we have a Intel TensorFlow install guide. I think you can Google search those exact terms, and it's the first thing that comes up. And we've gone into detail to show you how to build from source in an easily digestible way, so you're not pulling your hair out as you do it.
Thanks. Is MKL-DNN only for CPU or also for integrated Intel GPU?
Oh, this is hard to answer based on what's publicly available. The way I can say this is Intel has announced that we are working on hardware other than CPU, and we've officially announced that we have a discrete GPU that we're working on. Part of that announcement was that we were going to build software directly for that discrete GPU. And MKL-DNN is our #1 deep learning related math library, right? With the most resources to put towards it. I can't connect the dots any further than that based on what has and has not been told publicly, but all those things are true that I just said, and take them as you will.
Cool, thank you. Any requirement on CPU side to have significant benefit on Intel TensorFlow?
Can you say the question again?
Yeah, any requirement on the any requirement on the CPU side to have a significant benefit on Intel TensorFlow?
Yeah, so I covered these instruction sets in this talk in the hardware side on purpose, because a lot of our optimizations are targeted at the wider vector registers that came around in the Skylake generation. So all that heavy vectorization is best used on a Skylake or newer processor. Our kernels aren't going to fail on older generations, but they're just not optimized, right? We have reference versions of all the pieces of math that run, so you're not going to fail, but you might be getting, let's say, if you're familiar with scikit-learn 4 or 5 years ago, before they started offloading a lot of their calculations to the C layer, you'll get those kinds of implementations to where it doesn't error out, but it does it the most naive, way, because we just haven't really, we haven't really focused on those older generations. But anything 512 and above, we really we hit it hard. If you have a newer processor that is maybe AVX2, you'll also get very good benefits. So I don't want to say it's a requirement to go for the 512 vector register and instructions, because AVX256 is also going to benefit from these. But a processor from 15 years ago is not going to be targeted very well with these types of accelerations.
Great, thanks. This one's a little long, but let's tackle it. We have a DNN inference code of our own written with MKL, not using TF or other T-kits. It sounds like a big part of the speed up you get is in the code on top of MKL-DNN, and that is something we'd have to write ourselves so we can benefit from it, unless using a toolkit, right?
Yes, I believe the questioner is on the right track. So the framework teams work, and like I said, closer to the solution space. So they're building routines that think of it like large wrapper functions or helper functions to help users get easy access to accelerations. That's the framework side. But MKL-DNN is a primitives library. It's just primitives. You own all the orchestration around the primitives, and you own making decisions on format and data types. And that's how it's written. If you want to use it directly, you'll have to be in that space of writing all the orchestration code yourself. Luckily, the MKL-DNN GitHub is not only looked at by the engineers, the developer team, but it's encouraged from their managers to jump on the GitHub forum or the GitHub issues and answer questions directly, because they know that it's a hard library to use. It's complicated. So if you go there, if you have issues trying to write orchestration around execution of MKL-DNN code, go there and ask questions. If I don't answer it, the dev team will answer directly. So it's as close to the source as you can get. Also, there's a new version of MKL-DNN coming out, and there are some changes to the API, and it's coming out very soon, in a matter of weeks. And with that, we have a full new piece of pieces of the developer guide that my team is helping with and sort of leading on. So just like in this talk, I try to focus on what the user is going to see when they come to our websites, and what the user wants. All the new documentation for MKL-DNN, or at least in the developer guide, is going to be targeted the same thing. So maybe it's, in a few weeks when that's released, it might be a good thing to read if you're trying to use MKL-DNN directly, and maybe develop some intuition on how to write the orchestration code quicker, with descriptions from me and my team and Louis, who was answering questions on the Q&A section. But we know it's hard to use, and it's something we're working on with the developer guide.
Thank you. What's the best way to train a network on a Xeon server? My network takes 3 days to train on it, but with NVIDIA's GPU, it takes 7 to 8 hours.
The best way. So, like I said, for Caffe and in TensorFlow, we have Intel has decided on what we want to recommend for distribution library. So if you're going to use, I don't know which framework you're using, but let's just say you're using Caffe. Get Intel's version of Caffe and get our recommended distribution strategy for that, which is our MLSL library, and set it up on your cluster and run. If you're not using those optimizations, you don't frankly have a chance to run fast. So start by getting Intel's Caffe, get our MPI, the one we recommend, the MPI library we recommend, and run it a few times, right? If you're working on a cluster, you probably have HPC experience, and you probably can do some tuning yourself. But after that step is done, come to us on the forum and ask us questions. Like I said, we're going to give high-touch support on that forum. We're going to try to be responsive. We're going to push very heavily to be responsive to you. So if you have questions, bring it to us and ask us.
Great, thank you. Should I use Intel Optimize TF or OpenVINO for final model deployment?
Intel's answer is we built OpenVINO to do inference and to deploy, and we believe it's the best. So that's going to be what you see from press releases and websites, and it's true. It's a very fast way to do inference, and we take model interchange formats into it, so anybody can use it, no matter how they train their model. But we're not putting all our eggs in that basket. So a big part of the TensorFlow optimization is on the inference side. So I can't tell you, where to run your code because maybe you prefer TensorFlow, over other frameworks. That's your decision. But we're not forgetting about the inference side of TensorFlow. We are working on it. So if you want to stay in TensorFlow to run your inference in framework like that, you'll still get our accelerations.
Great. Looks like we're at the top of the hour, so I'm going to ask one more question before we wrap it up. I've seen this a couple times. Is Intel TensorFlow implementation supported by Keras?
Supported by Keras. So Keras is a high-level API on top of TensorFlow, and we write to the TensorFlow layer, so it should not break anything with Keras.
Great. Well, thank you, Nathan. Thank you for answering all those questions, and thank you, Louis, who's behind the scenes frantically typing away at just a ton of questions that came in. And thanks to everybody for showing up and asking questions and being interested. That'll do it for today, and that concludes our webinar. Thanks for joining us.